We're going to continue looking at some graphical representations of data in section 13.1. Example number 6 looks at the mean temperature that was recorded in Los Angeles for 50 days, and a histogram was then created. Use that histogram to answer the following questions. There's a little note here that says the x-axis does not use midpoints or class boundaries. As a result, this is not a perfect histogram, but it is useful for answering questions about how to read a histogram. So when you are creating a histogram, I would like you to use proper notation, which means using midpoints of classes or class boundaries on the x-axis. However, this one suffices to give us an example of understanding how to look at it and read it. So part A says, what percent of the days had a mean temperature of less than 70 degrees? What we need to do is we need to decide, well, how many items are in each bar? So if we look at the very first bar over here, it looks like there are approximately one value in that one. And then the second bar looks like it has a height of about 6. So we're going to say this has 6. For the next bar, I would say that has a height of about 8. And for the fourth bar has a height of 10. Since it said 50 days, we could go through and we could also look at the next couple of bars and see if it all adds up to 50. So I would say that it looks like these two bars have a height of 4. This one has a height of 8. I would say this one is at 3. These are 2, and these are 1. So if we added all of those together, we should get 50. 8. Let's see. 7 and 8 is 15. 25. 33, 41. Yes, so with those numbers, we add them all up, it does equal 50. So therefore, our heights of our bars are accurate. And so it says, what percent of the days had a mean temperature of less than 70 degrees? Well, 70 degrees is right here. So we are looking at these first 4 bars. That is where we have values that are less than 70 degrees. So we have 1 item in the first bar, 6 in the second, 8 in the third, and 10 in the fourth. So if we add all of those together, we end up with a total of what? 18, 19, 25. And in order to figure out the percentage, we would take that and divide it by the total number of items we have. Well, we happen to have 50 items, so the math on this is relatively easy. 25 out of 50 is 0.5. So 50% of the days had a mean temperature that was less than 70 degrees. B said, what was the highest mean temperature? So our highest mean temperature is going to occur in this last bin here. Notice this histogram has a bin that does not have any values in it. And when we look at that bin, let's see, it looks like that bin is somewhere between 86 and 88 degrees. So we know that the item that is in that bar could be 86 degrees, 87 degrees, or even 88 degrees. So we don't know for sure what the highest mean temperature is. That's a downfall of a histogram or of a frequency distribution, is that we have the data, but we don't know the actual data points. And so as a result, we know a range of the values that could have, but we don't know whether it has the lowest value in that bar, the middle value, or even the highest value. So we just have to give a range of values. So we would say somewhere between 86 degrees Fahrenheit and 88 degrees Fahrenheit. On page number 8 at the top, it talks about how to describe a distribution of a quantitative variable. So if you have a histogram, how can we describe that histogram? And so there's two things that you kind of want to look for. The first one is you want to look for the overall pattern and for striking departures from that pattern. And then we describe our overall pattern using this idea or this concept of SOCs. So SOCs is some characteristics of data. And when we look at SOCs, you want to describe four things. We want to describe our shape. We want to describe our outliers, we want to describe our center, and we want to describe our spread. So we're going to start off with shape. When you describe the shape, you want to concentrate on the main features, or also talk about symmetry or skewness. Outliers are going to be values that fall outside of our normal kind of range of data or the overall pattern. And so if you have a lot of data that's clustered together in one area and then another data point that's far away from it, we would call that an outlier. Next is center, and we're going to get more into what it means to talk about the center of the data, but right now we're just going to base it on where the middle of the data seems to lie. So with a histogram, we could kind of give an estimate of where that center would be. Later on, we're going to learn how to do some actual calculations for center of our data. And then spread, our book uses the word variation, but spread, you want to concentrate on if the data is spread out or concentrated in one area. In terms of shape of data, we have a couple of different types of shape that we tend to talk about. So a distribution is said to be symmetric if the right and the left-hand sides of the graph are approximately mirror images of each other. So if we look down at the bottom, these example 7, these different shapes, the first one would be considered symmetric. The second one would also be considered symmetric. There's a special word we use for it. We call this uniform, since all of the bars are the same height, but we could also call it symmetric. A distribution is skewed right or right skewed if the right side of the graph that contains the half of the observations that have larger values is much longer than the left side. So essentially what that means is most of the data is on the left-hand side. So most of the data is on the left. So if we look down at example 7, that third example, most of our data is on the left-hand side. We have a much taller bar here at the beginning where there is a lot of our data compared to the other end where there's very small amount. And another way to kind of think about it is if we can kind of draw, and if we have a tail that kind of goes down on the right, then we could say that that is skewed right. And a distribution is skewed left. Or left skewed if the left side of the graph is much longer than the right-hand side. So this next one down here in example 7 would be skewed right, since most of the data is going to be on the right-hand side. So most of the data is on the right side. And if we look at the other ones down here in example 7, this one here is also skewed right. And the last one, we would call that one, we would say that it's double peaked because there kind of are two high points. So we could say this is double peaked. I would also call this one kind of roughly symmetric. Because if you kind of find the center, which is about right here, notice that on either side you have these two bars are approximately the same height. These two bars are about the same height. And as we move out, you have the ones that are about the same as each other. So we could say that it is roughly symmetric. It's not perfect, but approximately or roughly symmetric.